Again, the main motivations for using multiple regression analysis is to relax the zero conditional mean assumption by incorporating more independent variable, right? By incorporating more independent variable. Multiple linear regressions also allow researcher to use more flexible functional form. For instance, quadratic functional form, sphere, power 2. All right. So the equation of multiple linear regressions is very similar to simple linear regressions. The difference is that we have multiple x, we have multiple independent variables, we have multiple explanatory variable. We still call y dependent variable, explain variable, or respond variable. We still call the epsilon as error term, disturbance, or unobserved variable. Beta 0, we still call it intercept, and beta 1, beta 2, until beta k, we call it slope of parameter. We call it slope of parameter or error term only for populations, but we will call it estimate or residual for sample. All right. So last week, what we discussed is also how to interpret multiple linear regressions by holding all other explanatory variables that included in the model. All right. But again, with multiple linear regression, we still assume that the error term is fixed, which is depends on zero conditional mean. If zero conditional mean assumption is met, of course, we obtain unbiased estimate, our interpretation is correct. But if zero conditional mean assumption is violated, the interpretation is incorrect, we obtain unbiased estimate. All right? And we did discuss about the property fitted residual, which is quite similar or the same to simple linear regressions. We then discussed goodness of fit or R square. You guys know how to interpret the R square, right? So basically, R square is the proportion that this multi-regressions model explain variations of dependent variable. All right. Again, we then discuss the 4 assumptions, but unlike simple linear regressions, the 4 assumptions in multi-linear regressions is slightly different. We still have the same assumption 1 to assumption 2, which is linear in parameter and random sampling, but assumption number 3 is something different from simple linear regression. Assumption number 3 is perfect collinearity. When we have multiple independent variables, we need to make sure that all included independent variables are not perfectly correlated. Right? I did give you 2 examples of small sample. So the perfect collinearity between expenditures and income. So for instance, if I interview 100 students about the income and the expenditure, if all 100 students spend all their income, we say that these expenditures perfectly correlated with income because all the income are spent. All right. Another example is the perfectly correlated between 2 variables like as share A and share B, and that sum of share A and share B equal 100. What we say here is that if you know share A, you can compute share B. But if your model includes both share A and share B, they both are perfectly correlated, right? So it's better not to include the two variables that add up to 100%. But here in this case, for the second example, if you use expenditure, the amount spent on A and amount spent on B, they are different story because they not add up to 100%. They are correlated, but not perfectly. All right. Assumption number 4, as always, is about zero conditional mean, meaning that the other independent variable that affect your independent variable of interest and dependent variable are not in unobserved variable, are not in error term. All right. If there are some variables that are still in error term, zero conditional mean is violated. If all variables that affect your independent variable of interest are included, then there is no issue of zero conditional mean. We also discuss a new term of zero conditional mean. So the variable, the independent variable of your interest that correlated with error term we call endogenous variable. And that endogenous variable, if there is a problem, we call it endogeneity. But if the variable of your interest is not correlated with error term, we call it exogenous variable, and that is exogeneity. All right. So endogeneity is another meaning of zero conditional mean assumptions. And just like simple linear regressions, if assumption 1 to 4 are met, we obtain unbiased estimate, meaning that the estimate from sample is close to the parameter of populations. Again, the meaning of unbiased estimate, meaning that the coefficient that you computed from the sample is representative, is very close to the parameter of populations. All right. And we ended at this point last week, and after break I requested you guys to work in group, and by today, before today lecture, you should have turned in your homework. So now let me have a quick look how many groups have turned in their homework based on your discussions. All right. So for now, only 6 groups have turned in your homework. So first, today we are going to continue our lecture on the second part of estimations. And then we will change atmosphere a little bit by having a group presentations. And let's see if we have time for a small hand-on exercise. Basically, this hand-on exercise I plan to do it on week 9. When week 9 or week 8, when we finish entirely the multi-regression analysis. But because I want to relate, to connect what we discussed in lecture to the application, so let's, if we have time, do some hand-on exercise or application with data a little bit. All right. So before we move on, any questions from last week lectures? Any question, class?
I have one question, sir.
Yep, go ahead.
Could you explain how to interpret the quadratic function again? How to interpret that?
The quadratic functional form is something that should not be interpreted now. It is another story. So but just to give you an idea. Wait a minute. Do we have yes. Can you see this the share screen? Just
yeah.
Right. So here, as you can see, the CEO 10-year is quadratic functional form. So in fact, to interpret this to interpret this quadratic functional form, you need to do what we call partial derivative. All right. So we mean that you need to do partial derivative given the COO 10 years. So in this case, the interpretation of this quadratic functional form of the COO 10 years, it will be equal delta 2. Wait a minute. If you do partial derivative to the COO 10 years, because your independent variable of interest is COO in 10 years, then we will have delta 2 plus delta 3 COO 10 years. So the interpretation of this depends on the value of COO 10 years, and the quadratic functional form will tell you that if if there is a positive sign, it means that when the COO 10 years is increased, it will increase up to 1 point, and you will find the optimal value, then it will be decreased. All right. Here, just to answer you very quick, but we are not going to focus on this now. When you read some literature that, for instance, your research question is going to employ quadratic functional form, then you will obtain more idea. But a quick answer to you is that this interpretation relies on the value of COO 10 years. Then we will find what is the optimal value of COO 10 years, meaning that the increase of COO 10 years will also increase the salary, but not always. At one point, at optimal point, it will no longer increase, and that it will return back to its original shape. Is that all right, David? Yes, David?
Yeah, sure. Loud and clear.
Right. So I believe that my quick answer is not that clear enough. But again, I don't want to confuse many of you, since David asked you, I just give you a quick answer. And that, if you get the point that I explained, when you do more reading in a similar field that you are going to use quadratic functional form, you will see that. All right. Or if you guys are going to use quadratic functional form in your group assignments, feel free to discuss it and ask me how to interpret it again. All right. We can go together. Don't worry. All right. Any other questions? All right. No. So let's continue our lecture. Today we are on week 7. All right. Still on multiple regression analysis. All right. Before we move on, can you guys quickly confirm? Can you see the share screen and clearly hear me?
Yes, teacher.
Right. Thank you. So, guys, feel free to drop your question in the chat box. All right. If you don't want to ask, if you don't want to reply me, feel free to drop your question in the chat box. Don't be silent. All right. Don't be silent. But anyway, if you engage with me, I am very much appreciate it. I don't want to be like a stupid person talking alone. Providing a lecture is just like making a conversation. We need audience, and we need to talk. between two people. All right. So join me. Don't stay silent. All right. So let's continue the second part of the estimations in multiple linear regressions. I just quickly recap what we learned, what we discussed last week. All right. So at the end of the lecture from last week, you learn again that if the assumption 1 to 4 are met, we obtain unbiased estimate. We obtain unbiased coefficient. All right. Today, let's continue. All right. So, since we have multiple independent variables, then we incorporate many independent variables into the model, which we aim to relax to address the zero conditional mean assumption or to solve endogeneity problem, we may at some point include a relevant variable into our regression model. We may include a relevant variable into regression model. What happens if we include a relevant model into the model? When we say a relevant model class, a relevant independent, meaning that it should not be in the model. But at some point, because you are afraid that if you do not include it in the model, you may violate zero condition only. So you want to include many multiple independent variables as much as you can. So unintentionally, you include the irrelevant variable. So that what we mean is that when you include the irrelevant variable, for instance, if you are interested on the effect of X-ray, all right, of this X-ray, as you see the red highlight here, all right, you want to estimate the effect of X-ray. Oh, sorry, you want to estimate the effect of X1 on Y, but unintentionally you include X-ray. What happened? Will the model produce unbiased estimate? When you include X-ray into the model and this is a relevant variable, normally the expected delta hat 3, all right, is normally equal 0. So in terms of estimate, there's no problem. It means that even though you include, all right, a relevant model, a relevant regressor, a relevant independent variable, you still obtain unbiased estimate as long as assumption 1 to 4 are met. However, when you include a relevant variable, it may increase sampling variance. When it increases sampling variance, you will obtain biased standard error. Remember, I always told you from the simple linear regression that you need to obtain unbiased estimate and unbiased variance or standard error of the estimate. All right, but here, when you include a relevant regressor, you of course obtain unbiased estimate, but you obtain large or say biased standard error of the estimate. All right, it may not affect your estimate, but it affects standard error or the variance of your estimate. Right? So there is still an issue. All right. So here, if you look at here, you have to trade off. Either you want to include a relevant variable or not to include a relevant variable. But if you include, you address the issue of omitted variable bias. But another issue emerge. All right. But at some point, if you do not include a relevant variable, but it may be a relevant variable, then you violate zero condition only. We will discuss the trade-off. We will discuss the trade-off between including or not including. But assuming that you believe that this is a relevant variable, all right, for the first case, because you want to make sure that zero conditional mean is met, you include a relevant variable. But since you want to make sure that this is not a relevant, this is a relevant variable, so you include it. So if you exclude it, if it is a relevant variable, that's okay. But at some point, unintentionally, you omit or exclude relevant variable. Or say because of data availability, you will not be able to include relevant variable. For instance, you want to estimate the effect of education on wage, but there is no data on ability. There is no data on ability. So in this case, you have a problem of endogeneity or zero conditional mean assumptions is violated. In other words, we call it class. This here, we call it omitted relevant variable. So in the future, when you read any paper, This zero conditional mean assumptions can also sometimes called endogeneity, can also sometimes called omitted variable bias. All right, so there are three terms. There are three terms: zero conditional mean, endogeneity, and omitted variable bias. But just to give you an idea, endogeneity, the meaning is more than more than zero conditional mean assumption. But for now, you just need to know that they are the same, right? For now, you just need to know that when we say there is endogeneity, meaning that zero conditional mean assumption is violated. When we say there is omitted variable bias, meaning that your zero conditional mean assumptions is violated, meaning that you cannot make causal interpretations. All right, what do we mean by omitted relevant variable? For instance, here, our true model, all right, our true model, when we want to estimate the effect of x1 on y, we also have to include x2, because here x2 also affects x1. So true model is that we have to include both x1 and x2 in the model. But what happens if you exclude or omitted x2? All right. So for instance here, if you omitted x2 from your model, you will have an estimated model where you only have one independent variable. So our question is, will we receive delta 1 equal delta alpha 1? All right. Here, as you see, true model, we have two independent variables, h1 and h2. And we assume that h2 also affect h1, correlate with h1. But because of data availability, because at some point unintentionally you omitted h2, you only have h1 in your model. Then we write equations, differently, so that we can distinguish the difference. For true model, we have delta 1. For the estimated model, we only have alpha 1. The question is, will delta 1 equal alpha 1? If alpha 1 equal delta 1, we obtain unbiased estimate. If we obtain alpha 1 different from delta 1, we obtain biased estimate. And here we are going to explain you more in equations. What do we mean by zero conditional mean in more detail here? Did you get my point here, class? If x2 is omitted, it means that now x2 is in this error term, right? In this error term. In this model too, in this estimated model, we don't have x2. So x2 is in error term. Our main question is, will we get unbiased estimate, or will alpha 1 equal delta 1? Because here, true model, we have two independent variables, but estimated model, we only have one independent variable. Will alpha 1 equal delta 1? You don't have to answer, but I just want you to know what do we mean by zero conditional mean assumption. What do we mean by endogeneity? What do we mean by omitted variable? Meaning that our estimated model here already omitted x2. When we omitted x2, meaning that x2 is in error term because we do not include it in the model. So meaning that our h1 is endogenous. Are you following me? I hope you guys follow what I am saying. I try to use different term so that you can familiarize yourself to different term. All right? Questions?
So
All right? Yep.
what does it mean when it increase the sampling variance?
When it increase sampling variant, meaning that the variant your estimate is getting bigger and bigger, larger and larger. And your standard, as a result, your standard error of estimate is also become larger and larger. You remember that that's very related to statistic review 1. Statistic review 1, we discussed about sampling and sampling distributions. And during that statistic review 2, we discussed about sampling and sampling variant. All right. So when we say sampling variant here, we refer to the variance when we have multiple data sets. And that variance is become larger and larger. Quickly review statistics too, so you have more idea about the sampling variance. All right, but here, if you don't remember, just a quick note that when this sampling variance increase, the variance of the estimate, the standard error of the estimate become larger. All right, become larger.
Right. Just a quick review. So mean that it increases in the bell curve, right?
No. The variance is the delta. The delta square. All right. Okay. It's mean that normally the variance is, if it normally distributed it like this, but when it increases the variance, sampling variance, meaning that it get farther from the population mean. It get farther and farther like this when it increase sampling variance. All right. For instance, we want to have this estimate is true, but when we include a relevant variable, the variance of this estimate become farther and farther from the beta 3. The beta 3 here is the parameter of population. You get what I mean?
Thank you, Loud. Okay.
All right, good.
Teacher, can you explain the omitting relevant variable again?
All right. Again, what we say here, omitting variable class. Again, this omitted relevant variable is what we are going to talk here. What we are talking here is the same as zero conditional mean assumption and endogeneity here. If you look at this true model, this model 1 here, you see that there are 2 independent variables. All right. Here we want to estimate the effect of x1 on y. We want only to estimate the effect of x1 on y. But we know that x2 is also affect h1. So in this case, we have to, the true model is that we have to include x2 in the model. But the problem here is that we do not have data on x2, or unintentionally you exclude x2. So your estimated model, you only include h1. All right. So if you run regression using the model below here by omitting x2, we call it omitted relevant variable, because x2 should be in the model, but now you exclude x2, and we will discuss about its effect in the next slide. But here I just want to see to tell you the difference between the two models. The model 1, what we call true model. Model 2, we call it estimated model. And estimated model, we unintentionally or intentionally, because of data, we omitted x2. So x2 is omitted. That's what we call omitted relevant variable. Clear?
Teacher, in the moment that when you explain that when we omit the x2, then we have, how about when the estimated model, the alpha 1 and the true model beta 1, does it still the same or does it change?
That's what we are going to discuss next. Good question. Here, what we are expecting here is that if beta 1 equal alpha 1, meaning that this x2 is a relevant variable, because it does not affect your beta 1 at all. What we are going to discuss next, but what we are going to discuss here, we need to find out whether this alpha 1 in estimated model equal beta 1 or not. All right. If it is not equal, your estimated model will produce bias estimate, produced by us alpha 1, because what you want to find out is beta 1, not alpha 1. All right. So let me move next then. All right. So in order to understand the effect of omitted variable, because we believe that the x2 affects x1. So to understand the bias, right? Because, sorry, all right, we need to run as another regression of x2 on x1. All right. When we find x1 using x2 using x1, we can replace it into our true model. Our true model, and we have x1 and x2. When we rearrange it, class, all right? So this is the estimated model for estimated model. So what you found here is that now here is the alpha 1, all right? I do not go into much because sorry, I just want you to know the story, all right? So here, this is the estimated model. This is our true model, all right? Y equal beta 0, beta 1, x1, beta 2, x2. Where is x2? We get x2 from the above equation, all right? Plus u. Rearrange this equation for the estimated beta, for estimated model. We get this beta 1 beta here. This is equal. This is the alpha 0 in estimated model, and this is the alpha 1, and this is the w in simple. All right, here you look again at this model. All right, so in true model you have two independent variables, but in estimated model you have only one x, and then you have alpha 0, alpha 1, and this error term. So when you omitted x2 from the model, alpha 0 is different from beta 0. Alpha 1 is different from beta 1. In other words, if you look at here, alpha 1 include beta 1 and beta 2. And error term also bias. All right. You see that every estimate of estimated model, when you exclude or omitted relevant variable, it bias. All right. Here, if you look at the explanation, if y is only regress on x1 because we omitted x2, this will be estimated intercept, which is bias, because alpha 0 is the sum of beta 0 plus beta 2, this delta 0. Originally, we only need beta 0. And the alpha 1, which is the estimate that you guys want, that we all want, the estimate the effect of x1 on y. Now, originally, the effect of x1 is only beta 1. But now, because we omitted x2, this alpha 1 contains not only beta 1, but also plus beta 2, delta 1. All right? This is bias. The same also to error term. So if y is only regress on x, this will be the estimated slope of x1. So in conclusions, all estimated coefficient will be biased. This is the effect of omitted relevant variable bias. This is the effect of endogeneity. This is the effect of violating zero conditional mean assumptions. All right. So the story, what I want you guys to know is that here originally we want to test whether this alpha 1 equal beta 1, whether this beta 0 equal alpha 0, whether this epsilon equal this new error term. But as the result, when you omitted x2, all the estimated from estimated model are biased. In other words, if you look at the estimate of x1 that you want, they do not include the effect of x1, but also partially include the effect of x2, because beta 2 is the effect of x2. Oh, in the true model, beta 2 is the effect of x2. But because you omitted x2, this estimated model also partially include the effect of x2 into the effect of x1. All right, this is the result. This is the effect. This is what we mean by unbiased estimate when there is an issue of zero conditional means assumption is violated, when there is an issue of omitted variable bias. All right. So as you can see, alpha 1 does not equal, it's not equal beta 1. Alpha 0 is not equal delta 0 at all. It is bias. It partially includes the effect of X2, right? That is why I said from the beginning, you cannot make causal interpretation. You should not interpret this coefficient when you have a problem of zero, when you have the problem of omitted variable bias, or you violated zero conditional mean. Again, how do we know that there is an omitted variable in our model? Reading, let us tell you, will tell you. If you want to estimate the effect, wage, education on wage, what are the relevant variables that affect education and also wage? For instance, ability, all right? Ability. If you do not include the ability, it is not true at all. For instance, right? Questions? So this is the effect. The conclusion is that you will obtain bias estimate, bias intercept, bias slope of estimate. All right? That is the effect of violating zero conditional means assumption. Violating, when there is an issue of omitted variable bias, or when your variable is endogenous, you have the problem with endogeneity. All right?
Yes, sir.
Right. Next. All right, here's an example. All right, here's an example. Assuming the true model here, this is, guy, if you don't follow the math, look at this example. All right, assuming that we want to estimate the effect of education on weight, right? And we know that to estimate the effect of education on weight, we need to control ability, because normally, for instance, you want to know how much education affect weight. But normally, those who study, who got higher education, they have higher ability. Those who earn higher wage tend to both who earn higher education and also higher ability. So you need to separate the effect of education from ability. If you study microeconomic theory or textbook, you will see two different theories from education. We call human capital theory and signaling theory. Some firms select high educated people not because they are, they have higher knowledge, because they believe that those who highly educated, they have higher ability. Because when they know that they have higher ability, they tend to be able to graduate. So normally the education and ability are jointly affect wage. So we have to separate the effect of education and ability. So here in our true model, we need to have two different variables. One is education, as you can see, another one is ability. But assuming that you fail to include ability in your model, so you only estimate the effect of education on wage. So as you can see here, all right, as you can see, you will obtain bias estimate. Originally, you want to estimate only delta 1, but when you exclude, wait a minute, let me change color. All right. All right. Here, originally, you want to estimate the effect of education only. All right. In the blue highlight. But because you do not have enough data, all right, you do not have enough data, then you cannot include ability in your model. So when you exclude or omit ability from your model, the effect of education here is not only delta 1, but it's also contain delta 2, which is the effect of ability, and also delta 1, which is the relationship between education and ability. So as you can see here, your estimate that you obtain here is biased. your alpha estimated is biased. All right. So here, if you look at the text below, the returns to education delta 1 will be overestimated. It will be large because this delta 2 multiplied delta 1 is bigger than 0. You look at here, right? Because the new estimate contains delta 1 plus delta 2 multiplied delta 1, right? It's bigger than 0. If it is equal to 0, you obtain unbiased. But here, because this, right? This here is higher than 0, your estimate is biased because it is not only delta 1. It is the delta 1 plus delta 2 delta 1. All right. So it will look as if people with many years of education earn very high rate. But this is partially due to the fact that people with more education also earn more about on average because of their ability. All right, because you cannot separate the effect of education from ability. That's what it said. All right. Can you follow me? The effect of the violation of zero conditional mean, the effect of endogeneity problems, the effect of omitted variable bias.
Follow, teacher.
Yep. Question, David? Okay.
No, I'm good, yeah, I'm good.
Okay, good, good. So everyone, the question is if you include a relevant model, sorry, if you omit relevance variable from your model, how do you know that your estimate is bias here is larger or smaller than the true effect? All right, assuming that you delete ability from your model. All right, how do you know that the estimating by omitting ability is larger than true effect or smaller than true effect? In this case, you need to understand the relationship between omitted variable bias with dependent variable and omitted variable with your independent variable of interest. Here, you look at the below table. If, all right, remember omitted variable is x2, all right, it's x2. If this x2, all right, if this x2 has positive correlation between x1 and x2 has positive correlation with your dependent variable, the estimate here will be positive bias, meaning that it's larger than true estimate. It's bigger than the true parameter. All right? If omitted variable here is positively correlated with H1, but negatively affect your dependent variable, this is negative sign, this is positive sign, you will obtain negative bias. Negative bias here meaning that your estimate is lower than true parameter. You get smaller value than the real one. All right. When we say negative bias, it means that your estimate is smaller than the true population. When we say positive bias, it's meaning that your estimate is larger than true parameter. Another term we say upward bias. All right. This positive bias here, sometimes we call it upward bias, right? So this is upward, or negative bias we call downward bias. All right, downward bias. So if your model only contains two independent variables and one independent variable is omitted, you can understand the effect of omitted variable bias as long as you can expect the correlation. All right. For example, in our example here, we expect that ability and education is positively correlated. We also expect that ability positively affect weight, because ability positively affect both education and positively affect weight. We can say that the estimated when you omitted ability is upward bias, produce upward bias or positive bias, meaning that the estimate is larger than true parameter. Right? So the same story, if the correlation between x2 and x1 is negative and positive with dependent variable, we get negative bias. If it is negative between x1 and x2 and x2 negatively affect dependent variable, we obtain positive bias. This rule can only be applied if you use only two independent variables. All right, if you have only two independent variables. Question here? How are you everyone? So far, it's just the effect of omitted variable bias, endogeneity, or violation of zero conditional mean assumptions. Here, we just discuss further whether the bias here is positive or negative, whether the bias here is larger than what we expected or smaller than what we expected. Here, this rule can be applied only if your model contains supposed to have two independent variables. If there are more than two independent variables, the rule is difficult to apply. Questions?
So can bias equal 0?
If bias equals 0, we don't call it bias. That means our alpha equals delta 1. As we said here, if this delta 2 multiplies delta 1 here is equal to 0, there is no bias. If there is no bias, meaning that you have no problem. You have no problem of omitted variable, meaning that you did not have you did not violate zero conditional mean assumption. So there is no bias. Right? Do I answer your questions?
Yeah, teacher, thank you.
Right. All right. So let's move next. All right. Here, what we discussed so far, as I give you a note, the rule is only applied when you want to know whether positive bias or negative bias, only when we have two independent variables. More general case, if we have more than two independent variables, when you omitted one, for instance, x3, you still have x1 and x2. So no general statement possible about direction of bias. We cannot say the direction is positive or upward or negative or downward bias. All right. That rule, that direction can be tell only if you have two independent variables. All right. Next. All right. So last week, we already learned, just like simple linear regressions, if assumption 1 to 4 are met, we obtain unbiased estimate. And you just learned what do we mean by unbiased or biased estimate. All right. Mainly because of zero conditional mean assumptions. Now, remember, I told you that we need two unbiased. One is unbiased estimate, another one is unbiased standard error or variance. All right. So to obtain unbiased variance and standard error, we need another assumptions, just like simple linear regression, which is homoscedasticity. Remember what is homoscedasticity? This assumption was included in the quiz. You should be able to understand it now if you make mistake during your quiz. Right? So homoscedasticity assumptions tell you that variance of the error term or error variance is constant. It does not depend on any x. It does not depend on any x. it is not conditional on any x. All right. So here the variance of u given xi until xk should equal delta square. What it means is that it should constant. The variance should not correlate with any of the x. Zero conditional means it's about residual. Residual of error term should not be correlated with any x. But assumption number 5 is about variance. All right. Different. So this variance should be constant. Should not be conditional on any x. Right? For instance, variance of error term should not be conditional or depends on error term, depends on experience, depend on tenure. It should be always constant. All right? The assumption may be hard to justify in many cases. But don't worry, we'll have a topic discussed on this issue. Class, remember when assumption number 5 is violated, what do we call it? If it is met, we call it homoscedasticity assumptions. If it is violated, we have a problem of what?
Heteroscedasticity.
Right, good, David. We have the problem of heteroscedasticity, meaning that the variance of error term or residual here is conditional at least on any one of the x. All right. When x becomes larger, you have larger variance or smaller variance. All right. So as long as you understand the story, it's okay. If you don't remember much, I just want to highlight the story, the novelty. All right. All right. So in short form, we don't write it in detail. Just write variance error given xi. Right. Xi here it means that this is the what we call it. This is the scala or no, the vector, right? The vector scala. I forgot it. All right. So this is this xi here consists of x1 to xk. So it should be constant. It should be constant. If this assumption 1 to 4 is met, we obtain unbiased variance of error term and unbiased variance of estimate. Here earlier we discussed unbiased variance of error term. But because generally what we really want is unbiased estimate and unbiased variance or standard error of the estimate. So when we obtain the unbiased variance, the variance of that error term, we can construct variance of estimate. And that variance of estimate is equal this variance of error term divided by SST, and that SST is total sample variation. If you remember or you have a quick look on the simple linear regressions, the variance of the estimate is delta is this square divided by SST only. But for multiple linear regressions, we have another denominator, multiply 1 minus R square. All right. So the variance of estimate here, to make sure that we obtain the unbiased variance of estimate, it depends on three estimates. One is error term, variance of error term. Another one is SST, which is total sample variation and explanatory variable H, right? In this equation. And another one is R square. This R square is not the R square of the model, but this is the R square from a regression of explanatory variable on all Hg. All right. For instance, if you want to estimate the effect of the H1 on Y, then this R square is not from our simple regression, the regression from the dependent variable, but this R square is another regression. For instance, you will have, I should write here. So you will have the R square from H1, all right, equal delta 0 plus delta 1 H1. So it is the H2. So this is the R square on the correlations, the explanation from the independent variable. All right. So the relationship between among independent variable, not something with the dependent variable. These are J-sphere. All right, just a quick note. All right, so here we're gonna discuss how do we need to obtain the variant of to obtain unbiased variant estimate. All right, to obtain this unbiased variant of estimate, we need unbiased, right, variant of error term. We need unbiased SST, and we need unbiased, or let's say correct R-sphere. All right. So here, first of all, it's about variant of the error variant. As we just discussed, error variant can be obtained if assumption 1 to 4 or assumption 1 to 5 are met. All right. So normally the high error variant increase sampling variant when you have large. All right. When you have large here, when you have large variant of error term, of course you will have large sampling variant here, right? You will have large variant of delta J hat. All right. So a large variant necessarily make estimate imprecise. When you have large variant of delta J hat here, meaning that it is imprecise, it is not correct. So normally you cannot do anything to make sure that you obtain correct or unbiased error variant is to make sure assumption 1 to 5 are met. That is the way. All right. But for the SST, the total sample variation and explanatory variable, which is xij minus xj square, the summation here, that is more sample variation lead to more precise estimate. What do we say here? If we have larger denominator SST here, we have lower variant, right? Unlike this variant of error term, it has become larger, this variant of estimate is also larger. But here, if we have higher S estimate, because this is the denominator, we will have lower variant of estimate. That instead, we will lead to more estimate precise, right? And normally, to have a higher sample variation here, we need large sample size, right? It increases with sample size. So as long as you have large sample size, you have large SST. And when you have large SST, you obtain very good variant of estimate. All right. So the best way to make sure that you get the correct SST is to have large sample size. So now, based on these equations, the variant of error term, you will get it correctly if you have assumption 1 to 5 are correct. SST if you have large sample size. How about this RJ sphere? This RJ sphere, again, this is the relationship among independent variables. All right, the relationship, the explanatory variable among the relationship among the independent variable. How do we know it here? So the linear relationship, in other term, we call it linear relationship among independent variable. Linear relationship, not something about dependent variable now, is that you regress Xj, the independent variable of your interest, all other independent variable include a constant. All right. So just a quick note, what do it mean? All right. So R square of this equation will be higher, the better Xj can be linearly explained by other independent variable. What we say here is that when we have higher R square, our Xj is highly correlated with other independent variable. All right. If that is the case, sampling variant of delta J hat will be higher. So it is imprecise. So this problem is almost linear dependence explanatory variable. We call it multicollinearity. Now, if you look back at this equation, this variant of error term can be addressed if assumption 1 to 5 is correct. It's met. SST can be correct if you have large sample size, but this RJ sphere, it depends on your model, whether the correlation among independent variables is highly correlated. All right. Here, the highly correlation among independent variables, we call it multicollinearity. It is not the same as perfect collinearity. Two different issues. We will discuss this later. All right. So now we have another issue. If we want to obtain unbiased variance, if we want to obtain unbiased sampling variance for the OLS slope estimate here, all right, we need to make sure that there is no issue of multicollinearity. Let me insert here that perfect collinearity is the assumption number 3, something about unbiased estimate. But multicollinearity is the issue for the unbiased variance of the estimate or unbiased standard error of the estimate. They are different. Following me? So what we are going to do now is to discuss, to address another issue, which is multicollinearity. Multicollinearity. All right? In other words, here is that it's just very similar to a relevant variable class. Because you are afraid of omitted variable bias, you want to include more independent variable. So when you include more independent variable, you address the issue of zero conditional mean. You address the issue of omitted variable bias. But now multicollinearity issue is emerged. Right? So you need to trade off between multicollinearity issue and zero conditional mean assumptions. Now let me give you an example. What do we mean by multicollinearity? Again, multicollinearity is different from perfect collinearity. Perfect collinearity, two variables perfectly correlated. But multicollinearity, they are not perfectly correlated, but highly correlated. All right. When there is a high correlation among independent variables, you obtain no effect on your estimate, but effect on the variance of your estimate. Right? Here's an example. All right. Assuming you only want to estimate the effect of expenditure on teacher on the test score. But because you want to make sure that you obtain unbiased, you want to make sure that this beta 1 is unbiased, you also need to include expenditure for structural material. You also include other expenditure. All right? Here, you will obtain unbiased beta 1. But the issue is, normally, all right, normally, rich school, when they spend more on teacher, they also spend more on the other item. They also spend more on structural material. They also spend more on other item. So in this case, expenditure for teacher, expenditure for structural material, and other expenditure, they are not perfectly correlated. No problem of perfect collinearity, but there is a problem of multicollinearity because these three variables are highly correlated. All right, so let me read the text below. The difference expenditure category will strongly correlated because if school has a lot of resources, it will spend a lot on everything. As you can see, spend more on teacher, also spend more on structural material, also spend more on the other sector. So even though you obtain unbiased beta 1, but the variance of beta 1 here is light, is imprecise. All right. So here, let me continue reading. It will be hard to estimate differential effect. All right. It will be hard to estimate only the effect on expenditure on teaching. All right. Of the different expenditure category. Why? Because all expenditure are either high or low. All right. If in poor school, they spend low on everything. In rich school, they spend high on everything. So for precise estimate of the differential effect, when we say differential effect, the effect of one of the three or dependent variable, right? What you have to do is probably you need information about its situation where expenditure category change differently. All right. You need different data. The data that make sure that if schools spend more on teacher, they spend less on structural material, so that there is no high correlation among independent variables. All right. Otherwise, the sampling variance of the estimate will be large, will be imprecise. All right. Questions? How are you now? So let me repeat. Perfect collinearity is the issue for unbiased estimate. Multi-collinearity is the issue for unbiased variant of estimate or unbiased standard error. When we have variant, we can find standard error. All right. So two different issues lead to different effects. All right. So let me finish this slide before we break the discussion on multi-collinearity problem. In the above example, all right, in the above example about expenditure on the test score, it would be probably better to lump sum all expenditure category because the effect cannot be percentile, right? So it's better to change your research question. It's better to change your research objective rather than to say, I want to estimate the effect of expenditure on teacher on test score, but it's better to say, I want to estimate the effect of school expenditure on test score. In that case, you do not have to separate, expenditure on teacher, expenditure on structural material, expenditure on other items, right? So the first way to address that issue in the example is to change your research question or objective, all right? Another case, you may need to drop some independent variable that may reduce multi-collinearity, all right? So in order to address the issue of about example, if you don't want to change your research question, drop expenditure on structural material or other item out of the model. But if you address the issue of multi-collinearity now, but this may lead to omitted variable bias. You see, you want to address the issue of multi-collinearity, but you have an issue of omitted variable bias. You have to trade off. You have to trade off. All right. All right. So only sampling variant of variable involved in multi-collinearity will be inflated. The estimated of other effect may be very imprecise. What we say here is that only the variant of the estimate of your independent variable is imprecise. Other variant of other estimate is okay. Focus on only estimate of your variable of interest and variance of the estimate of your variable of interest. All right. Again, multi-collinearity is not a violation of L-R3, right? In the strict sense. L-R3 is perfect collinearity. Two variables can be highly correlated as long as it's not perfect, not 100%. That's okay. But if there is no perfect collinearity, now it leads to multi-collinearity. All right. How can we detect multi-collinearity? I will take you in data. All right. Multi-collinearity may be detected through what we call variant inflation factor. Variant inflation factor. All right. Variant inflation factor. I will tell you how to do this in data. So normally, to calculate variant inflation factor is 1 divided by 1 minus RG squared. All right. And then we say there is a multi-collinearity issue if this variant inflation factor is higher than 10. I will teach you how to look at it in data application. All right. All right. Questions? How are you?
No question, Jack.
All right. So to trade off, sorry, here is the issue we have to look at the model again. We will break at 6:50 as usual. We have 2 or 3 minutes more. Let me finish this slide. So the variant of misspecified model. Earlier we looked at multicollinearity issue in general, but now let's have a look at both cases of both omitted variable and multicollinearity issue. All right. Variant in misspecified model. When we say misspecified model, class, misspecified model, it may be you include a relevant variable or you omitted relevant variable. All right. All right. The choice of whether to include a particular variable integrations can be made by analyzing the trade-off between bias and variant. Between zero conditional mean bias and variant. Whether you want large variant or you want unbiased of estimate. All right, to understand this, class, this is our true population model. To follow me, class, you can download the lecture note and follow me. All right, this is the original model, the population model. All right, and here we have estimated model 1 to make sure this is a estimated model 1 where, as you can see, we have y hat equal delta 0 hat plus delta 1 hat x1 plus delta 2 hat x2. This is the estimated model. This is the population. But here, and we have estimated model 2. And for estimated model 2, we omit x2 from the model. So we have y delta equal delta 0 delta plus delta 1 delta x1. Remember the notation, class, the symbol. When we say y hat, when we use hat, it is estimated model when we have 2 independent variables. All right. When we use delta here, this sign, this notation here, it means that the estimated model that has only 1 independent variable. Next, we want to compare the estimate and the variant. The estimate and the variant. All right. It might be the case that the likely omitted variable bias in a misspecified model 2 is overcompensated by smaller variant. So what we learned so far is that if you estimate using the model 1 here, you will obtain unbiased estimate, right? But you will obtain large variance. If you estimate your model using model 2, you obtain biased estimate but small variance. Following me? For model 1, you get unbiased estimate but large variance. For estimate model 2, you obtain biased estimate but low variance. Which one do you choose? Model 1 or model 2? All right, so you need to trade off. Either you want to address the issue of omitted variable bias. If you want to address the issue of omitted variable bias, you use model 1. If you want to address the issue of collinearity issue because you are afraid that x2 is highly correlated with x1, you use model 2. So which one you guys are going to use? You have to trade off. All right, let's discuss about this trade-off after the break. Anyway, before the break, does anyone have any questions? So far, we discussed the effect of omitted variable and multicollinearity. All right, again, omitted variable bias lead to biased or unbiased estimate. Multicollinearity lead to large or small variant. Our goal is to obtain small variant and biased estimate. Any question before we have 30-minute break before you have dinner?
No, Chair.
All right, so let's have 30-minute break, class. It is now 6:52. Please return back to our group at 7:23. All right, the 10-minute break start now. Hello, everyone.
Hello, Lakshmi.
All right. Thank you, Sai. Right. I guess you returned back to the group by now. Or probably some of you still having dinner. All right. So class, before break, we discussed extensively on the omitted variable bias in dark genetics, the zero conditional mean assumptions, which lead to bias or unbiasedness of the estimate. So you need to take extra care on that, right? And we then discuss the multicollinearity issue. Again, multicollinearity issue is different issue. It's different from zero perfect collinearity. All right. Here, as you see in these equations before the break, if we estimate this model one, if we estimate the model one, we obtain unbiased estimate. We relax zero conditional mean assumptions. The x1 is not endogenous, x1 is exogenous. But if you estimated model one, if there is a collinearity issue between x1 and x2, you obtain high or large variance of the estimate. All right. So with this model, model 2, all right, with the wait a minute, with the model 2, you obtain unbiased delta 1, but you obtain imprecise large variance of delta 1 hat. For model 2, when you omitted x2, all right, it becomes simple linear regressions. So in this case, you obtain this delta 1 delta, which is biased. It is not the same as delta 1 hat, but you obtain precise variance of delta 1 delta. All right, so this is a trade-off. The model one aim to address the issue of variable bias. The model 2 address the issue of collinearity, multicollinearity, but there is an issue of multicollinearity. All right, so let me finish this slide and then we will turn to the presentation. Then we will finish our the remaining slide. So again, if you remember, this is from the original variance, how we estimated variance. All right. So for the model 2, when we have two independent variable, as you see the head here is for model 1, where we have two independent variable. All right. So the variance of delta 1 hat. So the variance of delta 1 hat is calculated using this equation. When we have multiple independent variable, we have to include this denominator. But for the variance of delta 1 delta, when there is only one independent variable, there is no denominator of 1 minus r1 square. So multicollinearity, there is no an issue of multicollinearity issue with this model 2. Remember, when I say model 1, it means there are two independent variables. Model 1, there are only one independent variable. So what is the problem here? So if, right, in the case of model 1, where you include both, right, x1 and x2, in this case, all right, you expect that you will obtain the expected delta 1 hat is close to delta 1, and that delta 1 is the population's parameter. All right, so we obtain unbiased estimate. If that x2 is a relevant variable, all right? If that x2 is a relevant variable and delta 2 is equal 0, model 2 also produce correct estimate, right? Model 2 also produce correct estimate. But this variant from model 2, the variant from model 2, when you include the two independent variables, you see the variant of delta 1 hat is higher than variant of delta 1 delta, right? Because of multicollinearity, right? Case number 2. So in this case, right, should you include a relevant variable? If his base do not include a relevant regression, all right? Case number 2, trade-off between bias and variant, between multicollinearity and omitted variable, all right? So if you include a relevant variable here, right, delta 2 is different from 0, meaning that this x2 is a relevant variable. So if you run model 1, you will get that this expected delta 1 hat close to population parameter. But if you run model 1, the model 1 that exclude, that omit x2, the expected delta 1 delta is different from population parameter. Even though you obtain the variant from model 2 is lower than the variant from model 1. So caution is that bias will not vanish even like sample size. So in conclusions, remember class, from this example is that it's better to aim to address the issue of omitted variable bias. Try to relax to meet the assumption of zero conditional mean assumption. For multicollinearity issue, if there is a problem, you can address it by increasing like sample size, by having like sample size. Again, if you need to trade off between multicollinearity and omitted variable, choose omitted variable, all right? Try to meet zero conditional mean assumption. This multicollinearity issue could be addressed or solved by having like sample size. So that is why if you read good paper, good journal, or good research paper, when they run any type of regression, they always have high or like sample size. They always have like sample size, right? They always have like sample size, right? When they have like sample size, they don't have to care about multicollinearity issue that we discussed so far. But what they have to pay attention to is the omitted variable bias. Omitted variable bias cannot be addressed, cannot be vanished even though you have like sample size, all right? So always pay attention to omitted variable bias. Pay attention to endogeneity. Pay attention to zero conditional mean assumptions. That is the conclusions between the trade-off between multicollinearity issue and omitted variable bias. Question here, everyone? I just want to finish it first. If we come back later, you may forget it. Here, we just recently discussed before break, so that I hope that you still remember some things. Questions? Anyone have any questions?
No question, sir.
All right. Thank you, David. All right. So now let's change the atmosphere a little bit. Let's have group presentations. So far, how many groups submitted the assignments again? Six group, turn in your homework. All right. Now, I would like to ask for volunteer. Any group volunteer to present first your homework, your summary of the paper. Siddharth,
Group 1 chair.
Siddharth, what did you want to say? Are you which group are you from?
Yes, like we want to mention that group 1 would like to do presentation first.
All right, all right. That's fine. So group 1, please go ahead to present your homework. All right, go ahead. Floor is yours.
So, thank you. So our group will do presentation on the topic, the monetary policy. So the topic, the topic is about money supply influencing on economic growth wide phenomena of AEC count open region. So let me start by what is a monetary policy and is it important or not? So monetary policy is the manipulation of money supply with the objective of affecting macroeconomic outcomes such as GDP growth, inflation, unemployment, and exchange rate, something like that. So monetary policy is an important tool for maintaining economic stability and promoting economic growth. But do monetaries believe money supply affect economic growth or not? They don't. They don't believe that increase in money supply will affect GDP, but they believe that money supply too much will mainly affect on inflation. I mean the price in an economy. So, for example, in the 2009 financial crisis, like as we know, the worldwide recession led to a reduction in global GDP, like by minus 0.35% in 2009. And but Asian countries not only they use monetary policy, they also use macro uh, fiscal policy in order to support one another and to prevent inflation. And as an economy have been hit hard by the sharp slowdown in demand during the recession in 2009 as well. So they address the issue by using alternative policy like the measure like government spending on based on monetary policy to stimulate the economy uh, that they adopted, and along with the fiscal policy, so they don't use a monetary policy alone. So the expansionary money policy was enacted to stimulate economic growth by lowering interest rate and in order to increase the money supply. And this paper study about the relationship between money supply and economic growth in the context of the AEC countries. So therefore, my friend will continue from this. Thank you.
So moving on to objective of research. So next slide, please. So the objective of this study is to examine the relationship between money supply and economic growth of countries, of selected AAC countries. And in this study, employ an empirical analysis based on panel AODR approach by utilizing pool mean group estimator PMG to estimate the long-run relationship between money supply and economic growth during the period of 1995 to 2013. Also, the variable were used on this study, including of economic growth and money supply, which consists of money supply M1 and demand deposits DD of eight selected AEC countries, namely Thailand, Indonesia, Singapore, Malaysia, Philippines, Vietnam, Laos, PDO, and Cambodia. So moving on to the next slide, talking about literature review. Next slide, please. Yes. So the this question that change in money supply leads to change in real GDP. So the literature review in this paper shows us that the role of money in the economy has been in a long debate. Also, one argument is that monetary policy only affect price and not the GDP or the employment. So there has also been many study to analyze the relationship between money and economic growth, and also several studies conclude that there are indeed strong and mutual relationship between money supply and real GDP. However, if you look at the study that employ methods such as causality test and error corrections model, the result can be conflicts to the previous study and show us that money supply does not have a significant impact on economic growth. And some research paper would also go on to look at how inflation rates, CPI, and interest rate has impact on GDP. So I would like to give the floor to Diane. Thị Đề.
Move on to the next point is about the empirical result. So the result of the investigation, the relationship between the money supply and economic growth of the selection AEC country can be expressed like so. Can you move to the next slide, please? So the first table is the the first slide, like the first table. So the first table is the present the result of the panel unit root test of the three variables in the natural locate by various methods, namely LLC test, pretend test, Fisher test, type test using the ADF Fisher and the PP Fisher for the balls at the level, and the first difference of individual effect and individual linear trade. So it the result have indicated that each of the variable were not the same integrate of the integration level. So the GDP growth in the natural local data is stationary at level at 1% level of insignificant, but the money supply and the demand deposit in the natural local rate data were stationary at the first difference at the 1% level of the significant, and therefore it have indicated that each of the variable have a different integration level. So next slide, the table. Move on to the next slide. So the table 2. Yeah, so it's the result from the Pullman group and the Min group estimation for the ASEAN. So according to the table 2, the results show that from both PMG and the UMG estimation suggests that a positive relation between the money supply and the GDP growth from the selected Asian country, but demand deposit was negative with the GDP growth in the long run. So the long run coefficient of the money supply and the demand deposit was significant, while the MG estimate found that in the long run coefficient of all the variable that was mostly insignificant. So move on to the next table will present by the next presenter. Thank you.
So in this table 3, it is a result of a short-run coefficient by individuals country in AEC, or we call it ASEAN Economic Community. And those countries are Thailand, Indonesia, Singapore, Malaysia, Philippines, Vietnam, Laos, and Cambodia. So in this table, it shows an error correction term indicate that there were significant relations between these 7 countries in the table, except Singapore. So in short run, or we see in the first line that the money supplies and the demand deposit variables were significant toward GDP growth in Indonesia, Philippines, Laos, and also Laos, but demand deposit is the demand deposit, which is in line 2, is positive in this country. For Vietnam, money supplies was positive in the relations of GDP growth, but the demand deposit is in negative, which is different from the other 3. So therefore, this study can be explained that the increase in money supplies maybe cannot impacts on the in short run economic growth, just like Indonesia, Philippines, and Laos. Moving on to the next table, please. In these tables, it is a result on the Hausmann test. So the results show that with Hausmann test, to select the it used Hausmann test to select the most appropriate model to estimate the relationship between money supplies and economic growth within the selected ASEAN country. This study found that the Hausmann statistic, which is which use chi-square test, is the most suitable one, and the result is right 2.1. Therefore, it's concluded that it is the most efficient estimator under the nose hypothesis, and the Postman's group estimator is the most appropriate model. So moving on to the next presenter.
I'm sorry everyone for the technical error. So we missed on this part. So let's move back to the research methodology. So this study mainly focused on the relationship between money supply and economic growth in the ASEAN Economic Cooperation country. And further, for this study, they used the Pullman Group estimator to analyze the long-term and short-term relationship between those 3 variables, such as GDP growth rate, in which it represents as GDP, money, and demand deposit between 1995 to 2013. They use the Pullman Group estimator by combining both pooling average, and this estimate allows the intercept slope coefficient and the error variance to differ across the group. However, in order to analyzing long-term relationship between variables, we have 2 steps. And first, it involving with establishing the order of integration using the panel unit rule to check whether each panel data are integrated and it has a unit rule or not. Or in the other word, the null hypothesis was to test the panel unit rule in order to know whether the data are stationary or non-stationary. And second, considering the panel AODL approach by Pullman group and mean group to estimate the long-run relationship between money supply and economic growth of selected ASEAN Economic Cooperation country. So AODL, or we can call in forward autoregressive distributed lag model, is an ordinary least square based model which is applicable for both non-stationary time series as well as for time series with much order of integration. And this model takes a sufficient number of lags to capture the data generating process in a general to specific modeling framework. And for Pullman group method, it's a bit different from mean group method. So for the Pullman group method, it is a long-term coefficient. The long-term coefficient was the same for all units, while intercept, speed of adjustment, and short-term coefficient are different between units. However, mean group method, the coefficient of both the long-term and short-term intercept and speed of adjustment are different from every unit. And lastly, the hypothesis in this paper is to examine to decide the appropriate of this long-term coefficient with all units in the model. If this hypothesis is accepted, this means that the Pullman group is more appropriate as compared to the mean group. And yes, thank you. Let me give the floor for the next presenter to wrap up for the presentation.
Thank you, Dane. So this paper, as I have been presented, is to investigate the relationship between money supply and economic growth of the selected Asian Economic Community countries during the period from 1995 to 2013. They by using the Pullman Group estimator under what they call autoregressive distributed lag model. And the paper found that in the long run, between money supply and economic growth, it has positive correlation with GDP, while the main deposit, the the paper put is that DD have negative correlation with GDP growth. And this is our group presentation. Thank you.
Thank you. Group 1, class. Any question and comments for group 1? Thank you, group 1, for your effort. Let me honestly ask your group, to what extent do you understand the paper? Someone just tell me, don't worry. I just want to assess your understanding on the paper, because the paper use different data, use different model that I do not teach in the class. I feel that it is too difficult for you guys to understand it. Just honestly tell me how, to what extent your group or someone in your group can say, or Davin say, you would expect to understand. To what extent? How much?
Teacher, our group, right?
Either yourself or your group. To what extent do you understand the paper?
For me personally, I understand almost 50%.
All right, mainly result and interpretation, not the model part. Am I correct?
Model part, yes, not quite sure, teacher.
All right, class. If you closely follow group 1 presentations, you may find that the objective of the paper that they summarize or recap is not to assess the effect. Look carefully. Group 1, can you share the screen again and show them the objective? Show them the objective slide. All right. Just quickly show them the objective. All right. All right. Right. This slide. Just can you maximize or click slideshow? All right. All right. This paper, as you can see, it said to examine the relationship between money supply and economic growth, not to estimate the effects. If they start to estimate the effect, the objective of the paper is to make causal interpretation. They try the best to come up with a good model. But here, what they say is that they only want to estimate the relationship between money supply and economic growth. That is why in this paper, the author did not include any relevance independent variable. They only include, only just, 2 or 3 variables: money supply, demand deposit, and GDP growth rate. Let me tell you this. First, because of their objective, they do not aim to estimate the effect, because economists know that if you want to say you want to estimate the effect, this is what you want to make causal interpretation. That's quite hard. First. Second, because the nature of this data, they use panel data from 8 selected countries, and the data range from 1995 to 2013. All right. So normally in the future, we will simply discuss about panel data, and you will learn that in panel data, zero conditional mean can be addressed. The issue of omitted variable can partially address, not fully. I will tell you during the panel data model. But here, with panel data, we use different model. We don't simply use multi-regression model, just like you said, but every model was developed or extended based on multiple regression model. So in this paper, for instance, the author used ARDL. What is ARDL model? What is the full name? Group one? Does anyone know what is ARDL model is? The full name. That is acronym, right? ARDL. What is that ARDL?
It's called autoregressive distributed lag model.
Right. They use auto-regressive distributed lag, meaning that because the data, when they say lag, for instance, lag of year 2020 is 2009. Lag of year 2009 is 2008. So they use lag variable as an independent variable. But here I do not go into detail here. I just want to highlight that it is a little bit difficult for not only group one, but also you guys to understand this paper because we do not touch on panel data yet. And again, in this lecture, in this course, we will not discuss about ARDL model. We will not discuss about that. We only touch very simple panel data. Very simple panel data. We will discuss it on week 10 or week 11 or 12 something. All right? And again, because of panel data, because of the nature of their data, the author only aim to assess the relationship. If you remember from the beginning, I asked you guys to state that your objective is to estimate the relationship rather than effect. But if you want to say effect, it's okay. But I said it's better to say to estimate the relationship of this on that. Why? Because you cannot make causal interpretation. It's not really easy to make causal interpretation. All right, I will stop here. If I remember, someone raised hand. Saying group one, you can stop sharing your slide. Does anyone raise hand? Earlier?
Excuse me,
Yep.
like I confused to raise hand.
All right, that's
Sorry,
okay.
sorry.
That's okay. It's okay. All right. So again, group one presentation is a little bit hard for you guys to understand because they use different model and they use different data. And again, what we did study so far for simple linear regression and multiple regressions analysis, we only use cross-sectional data. All right. We only use cross-sectional data. Again, with panel data, the omitted variable could partially address. I will explain you during that course. All right. So that is all. But what you have to learn, what I am concerned about group one is that I expect you to get something from the paper. But since you use this paper, I feel like you guys do not benefit much from this paper. All right. So we will discuss it the following week because, as I said, after completion this course, you guys are going to expect to do your group assignment and you are going to run some regression analysis. And because we do not cover ARDL model, and since you presented this paper, pole regression, pole mean group estimator, we will not discuss that. If you want to follow this paper, something that we will not study in this course. All right. So if I remember correctly, in the previous homework, I asked you guys to formulate a research question or objective with a clear relationship in mind and think about the data, and that data should be cross-sectional data. All right. That is, thank you, group one. Now, any other volunteer? Any other group want to volunteer? We will have two groups today.
Like we are from group 3 and we want to volunteer.
All right. Thank you, group 3. You can start your presentation now. Floor is yours. can start now.
So, good evening, lecturer and classmates. We are from Group 3, and today we're going to present about our topic, which is analyzing the effect of income inequality on poverty. Next slide, please. Yes, and here is our content. Let's get started with the introduction. Next slide. The study focuses on the relationship between income inequality and poverty. And there are various ways of measuring income inequality, but in this paper, the Gini ratio is employed as the index to evaluate income inequality. And by understanding this measurement, it will be easy to deal with income inequality in society, hence narrowing the income gap as well as eliminating poverty. Next slide, please. And the literature review here, the level of poverty is the dependent variables, and while Gini coefficient as well as purchasing power, parity, adjusted mean income as independent variables. Moreover, this research paper aims to find out how poverty is influenced by income inequality. Thus, there is a correlation concerning the impact of gross domestic product, Gini coefficient as well as the rate of literacy, infant mortality rate, and Freedom House score on poverty. And that's it for my part. Let's move to the next presenter. Thank you.
Thank you. So now I'm going to talk about the experimental part. So for the experimental part, the author used two models in order to study the relationship between the income inequality and poverty. So for the first model that he used is simple linear regression, and for simple linear regression here, he used poverty as the dependent variable and the income inequality as the independent variables, which is measured using the Gini coefficient that has to show the degree in which family income deviates from income in an economy along with equitable distribution. And for the second model, next slide, please. And for the second model, the author used the multiple linear regression. So for multiple linear regression, it's actually similar to the simple linear regression, just that it added more element, it added more independent variables. So the independent variable that were added to the multiple linear regression here are the Gini literacy rate, log GDP per capita, freedom score, infant mortality, and high income. And the multiple linear regression here was used because in order to clear the bias that may exist in the simple linear regression. So examining poverty level literacy rate was a significant variable in this study, for it helps to evaluate the capacity of society workforce so that to improve its intellectual growth and economic opportunity. And the natural logarithms of gross domestic product per capita was also very important, for it evaluates the changes in the size of the economy associated to its population as well as its correlations with the poverty level. And besides, the Freedom House score tries to assess an individual levels of freedom rather than the government level in order to find evidence that proves that individual freedom minimizes the number of people living below the poverty level. And in this research, the author used the data from the World Bank's Development Research Group, and he actually extract the data such as the poverty headcount ratio, the Gini coefficient, gross domestic product per capita, adult literacy rate, and infant mortality rate. So that is the end for my part, and I would like to invite my teammate to talk about the next part, which is the result.
So for the results, the Gini coefficient was regressed on poverty as a way of demonstrating the effect of equality on poverty. So according to the table below, show the result for the simple regressions of the Gini coefficients in poverty. So in this study, the correlation coefficient is positive, meaning that if the Gini coefficient is increased by 1, it will result a positive change in poverty, which means that the number of people living in below poverty line will increase. Due to the simple linear regression model assumption, the result obtained by this model may be biased, not until there is no another variable. Next slide, please. So when it comes to multiple linear regressions models, it have to disclose all another thing being equal impact on property. So as the table below show the result of a multiple regression models, the equation below implies that an increase of 1 point in the Gini coefficients, it will result in a raise in the property ratios. Besides, the correlation coefficients of the level of literacy is minus 0.41, which means that an increase in literacy rate in society by 1 point will result in decrease in the poverty level by 0.41%. Moreover, the correlation coefficients on the log is negative, which is minus 5.05. So this is a strong negative correlations that show an increase of the gross domestic product per capita by 1% in society. So poverty level will reduce by 5.05%. So the Freedom House score has a positive correlation, which means that the higher Freedom House score implies that that is a higher level of poverty. So let's move on to the conclusions. So to sum up in this paper, the expression of the Gini coefficients as expressed in symbols and multiple layer regressions as expressed, they analyze and the relationship that exists between income equality and the level of poverty. And also, the study showed that the income is a significant factor that is affect poverty in the world globally. So it is a challenge for many countries that have faced poverty. So it shows those countries should focus more on improving the literacy rate, ensure that there is gross domestic product per capita growth, along with reducing equality and Freedom House scores. Moreover, in this paper, it considered that many variables that are associated with poverty in order to provide the potential policy outlines that the government would undertake. So to determine the importance of the income equality, literacy rates, Freedom House score, and the infants mortality rates, they can have the policymaker as well as the leader of the state to set and have the most strategic and effective plans that will combat poverty efficiently to improve the economic development. So this is the end of our presentations. Thank you for paying attention.
Thank you, group. Forgot the group number. Group 3. Please remain keeping your slide here. I will just want to highlight a few points to your classmates. But before I commenting or giving some comments here, let me ask to everyone. Anyone have any question and comments? Here in this presentation, I believe that you guys can follow it. It is very not easy, but it is to the level that you can understand it. It is, you can relate it to to our lecture. The paper start with simple regression, and then they say assumption is biased, and then they go to multiple linear regressions. All right, they go to multiple linear regressions. Any questions? Yes, no, okay. All right, class. All right, so what I want to highlight here, first of all, the topic and objective is slightly different. To me, this paper, they said they published in a journal, but my personal judgment, this is not a good paper. But for us, for our course, this is in the level that is acceptable that you guys can understand. But for publication, this is not a good paper. All right, first, what I want you to observe first is that the title of a paper is stating that analyzing the effect of income inequality on poverty. So they specify both independent and dependent. What is independent variable of interest? That is income inequality. What is dependent variable? Poverty. But if you go to objective, can you go to objective? Can you move slide to objective? All right. If you look at the objective, they tend to what they call it moderate. They tend to moderate the claim. Earlier on the topic, they said they want to analyze the effects. But for the objective, the study focus on the relationship. The term relationship, as I always said, the goal is not to make causal interpretation. It just want to know whether there is positive effect or negative effect. Positive relationship or negative relationship. But to analyze the effect, we aim to estimate, we aim to interpret causal interpretation. Slightly different here. All right. And what I want to say here is that I don't know, because the presenter, I also trying to look at the data based on your uploaded paper. I don't see the author explain much about the data. They only say they use the data from World Bank Group. All right. If they use the data from World Bank Group, what type of data? That is that data at country level? If you remember, Group 1 say they use panel data, each country from year to year. But here, probably I do not have enough time to look at the paper, and probably the Group 3 do not fully recap it, but we do not see a clear statement on data, whether this data is panel data, country level. Group 1 mentioned clearly that there is country level for each country from 1996 to 2015. But here, the author did not explain much data. Why it is important to mention data? The nature of the data tells you what is the nature of your econometric model. The nature of the data tells the reader what is the nature of the model. For instance, when you use cross-sectional data, as the reader, as the student who study econometrics, you know that they will use multiple linear regression, simple multiple linear regressions. All right, that's it, just like this paper did. But we don't know what type of data they use. If they use panel, that multiple linear regression is not enough. But that's okay. What I want to say here is that the objective of the author now, they tend to moderate their claim. They only want to know the relationship. All right. And what author did is, can you go to the method? The author start with the simple linear regression. As you remember, we first started with simple linear regression. Simple linear regression, we only want to know the relationship between one specific independent variable and your dependent variable. Here, the author did mention it. It's quite good. Thank you, Group 3, so that we can relate to our lecture. All right. The author mentioned that simple linear regressions could produce unbiased estimate of delta 1 only if all assumptions are met. But all assumptions are not met. That is, author decided to use multiple linear regression. Next slide, please. So with this multiple linear regressions, all right, the author incorporate more independent variable. Rather than using only one X of inequality on poverty, they also add, what are they? They add infant mortality rate. They add freedom of household. They add literacy rate. They add high income. That is a proxy variable. That's okay. they add another variable. All right. So the author did acknowledge the weakness of the OLS. But here, as you see in this paper, author only pay attention to the zero conditional mean assumption. The author did not mention about multicollinearity, but in the paper, the author did mention about perfect collinearity. Why? Because if the perfect collinearity is violated, the estimate is biased. The author did not mention about multicollinearity that we just studied, but the author did mention about perfect collinearity. The author mentioned that there is some correlation, but they are not perfect, right? So the author assumed that when they include more variable, the estimate that they obtain is unbiased. Class, I told you that even though you use multiple linear regression, you cannot make causal interpretation. Why? Because we cannot guarantee that all the relevant variables are not included in the model. But here, the author tend to interpret the coefficient of multilinear regression. Why? I will tell you next. Can you go to the slide on the result of the simple linear regression? Class, try to follow me. Here, if you look at the result, all right, Gini coefficient. You see Gini coefficient? Sorry, Gini and its coefficient, it is positive. All right. We do not study it now, but next week we will discuss. Next week and following week we will discuss about inference, where you will study t statistic in this table. You can see t score and p value here. For now, you look at p value is very low, 0.003. You will learn next week, but this is a good example to highlight it now. I may use this slide to explain you next week again. Here, if you look at the Gini coefficient, right, it has positive effect and p-value is very low. When you move to multiple regressions, again, can you move to multiple regressions? All right, next one. Yes, you look at here, the coefficients drop dramatically from 0.6 to 0.1. Why? It's probably that our estimate is upward bias, right? From 0.6 now to 0.1. If we use only simple linear regressions, we obtain unbiased, which is upward bias, positive bias, right? But here, because here if you look at the p-value, you do not study it now, don't worry. The p-value now is 0.2. It says that Gini is no longer significantly affect inequality. So since p-value is too high, all right, since p-value is too high, it doesn't matter what coefficient you get, meaning that conclusion will say that there will be no effect. There will be no relationship between Gini and poverty for multi-mode regression model. So if you guys have time, you can read this paper, all right, and look at the conclusion. Even though they found the positive relationship, but the author did mention in conclusion that multiple linear regressions produce insignificant, produce low t statistic, produce high p value. Because of this high p value, because of this low t statistic, you don't have to care about coefficient. Why? We conclude that this Gini is not related to poverty in conclusion. All right? In conclusion. That is why the author found that, to be honest, based on result, I did not read the conclusion. The author should conclude that the data suggests that, the analysis suggests that Gini coefficient has no relationship, has no, all right, no relationship with poverty. Because of this, again, we will discuss about inference next week. All right. Thank you, group 3. So as you can see, when you use multiple regression, one of the important note you see that coefficient is quite different, drop from 0.6 to 0.1. All right. So thank you, group C. Now you can stop sharing your slide. The takeaway for every group is that when you aim to use multiple linear regression, you need to also include other relevant independent variable. You only want to estimate the relationship between x1 on y, but to avoid zero conditional mean, to relax zero conditional mean assumption, to address the issue of omitted variable bias, you also need to include other relevant variable. So you guys already have research question and objectives. Now you have to look at the literature. What other independent variable should you include? For instance, if group 3 is going to do the same research, group 3 know that they want to assess the relationship between inequality on poverty. So other relevant variable, they can follow this paper first. If they read other paper, they find something new, they can add more. All right. So that is what you guys should do. Again, we do not finish multiple linear regression yet. At least 2 more weeks, we discuss about inference. We discuss about t-stars. We discuss about p-value. Again, I will use the group 3 presentations to discuss about this. And group 3, please remind me in the following week that I have to relate this with your group presentation. Thank you, group 3. That paper is good for your level so that you can follow it. Group 1, it doesn't mean that your presentation is not good. I mean that the paper is a little bit difficult for you to understand. All right. So for today, thank you, group 1 and group 3. Next week, I will ask another group to do the presentation. All right. We still have 10 minutes. But before I want to finish the remaining slide, let me ask anyone have any questions about the 2 presentation and about my comments. I hope you guys can relate the lecture to the presentation, to your group assignment. No? All right. So to save time, let me finish the remaining slide. All right. The remaining slide of our lecture. Can anyone confirm? Can you see the share screen?
Yes, teacher.
All right. So hopefully now your brain is not burning, a little bit relaxed. So far, before group presentation, I told you that between multicollinearity and omitted variable, try to address the issue omitted variable, meaning that try to include all relevant variable. Multicollinearity issue can be addressed as long as you have large sample size. That is why in the paper that group 3 just presented, they did not mention about perfect collinearity, but they mentioned about, sorry, they did not mention about multicollinearity, but they mentioned about perfect collinearity. Because perfect collinearity lead to unbiased estimate, multicollinearity lead to biased variant. All right. So aim to look at the unbiased estimate rather than variant. All right. So again, you already know that to estimate the variant of estimate of this beta 1, we need this variant, this variant of error term. And how to construct this variant of error term? That basically is the summation of square residual divided by n minus k minus 1. All right. What is that n minus k minus 1? We call it degree of freedom. What is n? N is number of sample, number of observation. K is number of independent variable that you included. 1 represent constant. There is always one constant or one intercept. All right. So n minus k minus 1. That's how you generate error variant. And again, if assumption 1 to 5 are met, we obtain constant variant. The variant is not conditional on any independent variable. And this variant, what we call unbiased estimator of error variant, it's also called standard error of regressor. All right, when we swear it is also called standard error of estimate. and the root mean square error. You will see it with the data. Data produce this root mean square error. All right. I will connect it to the data result when we come to the application. All right. So after we found the unbiased variant, right? After we obtain this, then we can generate standard error of delta G. Again, our goal is to obtain unbiased delta G and unbiased standard error of delta G. And to obtain this unbiased standard error of delta G, make sure we obtain unbiased variant of error term. All right, it is very important. All right, because the denominator can be reduced with like sample size, but this variant of error term cannot be addressed with like sample size. All right. Again, these formula are only valid under the assumption of LR1 to LR5 are met, specifically homoscedasticity. All right. So before we close, you should learn something new. So under the assumption 1 to 5 class, under the assumption 1 to 5, if assumption 1 to 5 are met, OLS estimator, OS, OD least square, OD the real least square regressions, we call it estimator, we call it base linear unbiased estimator. All right. If assumption 1 to 5 are met, you obtain unbiased estimate, you obtain unbiased standard error of the estimate. It is said that OLS estimator are best linear unbiased estimator. We call it blue, perfect model. All right. OLS is the perfect model compared to other model. All right. It's blue. All right. So when you include multiple independent variable, even though there is a multicollinearity, as long as assumption 1 to 5 are met, normally the variant of delta J is close to variant of the model that you omitted the variable. Don't worry about multicollinearity issue. All right. That is all for today, class. Any questions? So the takeaway for today's lecture is, again, assumption 1 to 4 produce unbiased estimate. Assumption 1 to 5 produce unbiased variant of error term, and hence produce unbiased standard error of the estimate. If there is an issue that you have to trade off between omitted variable bias and multicollinearity, choose the issue. Try to address the issue of omitted variable bias. Multicollinearity can be addressed with like sample size, with increasing sample size. Question, please. We have 2 to 3 minutes to go.
Hello, teacher.
Yep.
So when can we start writing our paper?
You can start as soon as possible. You can start now. Only the data part and analysis part. But again, your group assignment, you should start since I tell you, you should, organize introduction literature. You try to have a good term group, a paper, so that you have a higher score. We will sometimes discuss about data. All right. What should we do? As I told you, try to find existing data. If you already have the existing data, and if you, for instance, group 3, all right, they just find a paper, and that paper say they use the data from World Bank Group. If you guys can obtain data from World Bank Group, if you guys can have that data, then you can proceed to your analysis. For instance, you can replicate the paper, right? You can replicate the paper. That assignment is good enough, but don't follow the summary, everything. You try to read more than one paper. Is that clear, David?
So we can start to write the set methodology too, right?
Up to you. Remember the deadline of submitting the term paper. I don't know when. I forgot it up. I think it week 15 or week 16. You should start as soon as possible. All right.
For how many pages for the term paper, teacher?
No limitation. Style is yours.
Thank
I
you.
don't remember. Wait a minute. I don't remember. So please take a look at the syllabus. If the syllabus gives you any instruction, follow that. If no, style is yours. Clear, David? Have a look at the syllabus, the draft syllabus.
Teacher, thank you.
Right. So guys, don't forget about your term paper, your group assignments. If you have the data, you can proceed. But even though you have data, you may need to wait for the lecture step by step. All right. If you already have the data, follow the lecture. You can have introduction, let it tell you, and then you just need to wait for a little bit methodology and discuss and result. All right.
Teacher, I want to make sure that we can replicate other papers, right?
Right. For this paper, you can replicate. For this group assignment, so I want you to expose to the analysis. I want you to expose to how you are going to run to familiar with econometric model. Don't copy and paste. When I say replicate, I mean about the analysis. It's about analysis. For instance, use the same independent, dependent variable, but you probably need to find the data. If they choose only 8 countries, you need to increase to 10 or 11 countries. Is that clear a bit?
It is. Oh, one more thing. Can we use longitudinal data set?
Of course you can, but the point here is that we do not study yet. So I am afraid that you cannot do it now. All right?
Oh,
I am afraid that it may need time because we do not study yet. That is why I suggest every group to use cross-sectional data. So my expectation from your term paper is just to run multiple linear regression using cross-sectional data. And make sure that you know how to interpret the data. Right? So that is all for today, class. Next week we will continue the second, the also multiple linear regression, but inference part. We will discuss about t-static, probably p-value. All right, and we will continue the group presentation next week. Again, don't wait until you finish the lecture. Start your group assignment, your term paper, group term paper as soon as you can. All right. That is all for today, class. I see you next week. Stay safe and take care. See you.
Hello, Chair. Can you tell me again? When is the deadline?
I don't remember. You can have a look at the syllabus, on the syllabus. So one, clear?
Yes, sir. Thank you.
Right. The syllabus should tell you at the course outline. I should have the deadlines there. If you cannot find it, ask me next week. I will confirm it again. All right.
Teacher, there's no deadline in the course syllabus.
Really? Did you have a look at the course outline?
Yeah, only the day for presentation date, the last 2 weeks of our semester.
All right. We may subject to change the date if time is not enough for everyone. Wait a minute. Let me have a look. Right. There is no date yet. Wait a minute. Let me go up. Look at the. Wait a minute. Let me go down. The teaching material. The research paper. Group. Research paper. All right. There is no deadline yet. I will inform you the deadline next week. I will have a look. To give you a proper date because you also need to prepare for your final exam. All right. I will come up with the deadline next week. All right. Thank you, everyone. See you next week. Take care.
Goodbye.